Hello, my friends, family, former lovers, whoever is watching this video. Today I'm covering homework 6, the various problem types. I'm not covering every single problem, but I'm covering every single problem type, except for number 6. I think number 6 is fairly straightforward, but I might cover it at the end. We'll see. Also, feel free to put this in 2 times speed because I talk a little bit slow. Numbers 1 through 5 pertain to schematic models. The schematic models are composed of some illustration that we're supposed to derive some form of differential equation. There's a couple there's a couple conventions that we need to understand before we jump in. The first one is that everything happening to x and y is a rate. That means x is really dx of d of t, and y is really dy of d of t. There's nothing really here that would suggest that it's a rate. It's, as I said earlier, it's just a convention. Um, so looking at dx of dt, we'll notice a couple things. The first one is that there's only one source of y and there's two sources of x. It's not important here, but it'll be important for the next couple problems. Likewise, for dy of dt, there's only one source of x and there's two forms of y. So when you're composing your models, understand that you're really just characterizing how each component is changing with respect to dx of d of t. And it's really quite straightforward. So with dx dt on the left, we have 1.7x leaving. So that's minus 1.7x. This has a value of 0, so we don't need to worry about it. And then this also has a value of 0, so we don't really need to worry about it. And that's going to give you dx dt is equal to negative 1.7x. That's your first guy. On the right-hand side, we have dy of dt. We have 1.7x coming in, but also on the bottom, we have 0.2y leaving. So if we characterize that, dy of dt is equal to 1.7x minus 0.2y, which makes this guy down here, which gives us kind of a handy-dandy little system from which we can make a matrix. And this is important for satisfying this component. It wants us to characterize the equilibrium as a type of some type of node. So in order to do that, we need our eigenvalues, and in order to get our eigenvalues, we need a matrix. But as we know, this guy, and this guy, and this guy, this guy, and this guy, and this guy, and this guy, this guy. And then obviously you have your x and y. X and y makes a dot product with each fellow. You have your matrix. It's pretty straightforward. Everyone can probably do this by now. There's no really need to elaborate. Same thing with the eigenvalues. Everybody knows the formula, and then you set that John equal to 0, and you find your fellows. And I understand that everybody has different math problems. The numbers, the types of problems are all the same, but the numbers are likely different. This is what I got from mine, and you'll probably get negative values as well. I got two real negative values. Over on the bottom right here, I have a decision tree. It has some insight as a means of determining what type of node you have. So first off, is it a node? Sometimes it's going to tell you off rip that it's not a node, and you should know that a saddle point is not a node. So if you know that it's not a node, you're probably dealing with a saddle point. But sometimes you don't know, you kind of have to figure it out, which is what we're doing here. You have your eigenvalues right here and right here. Oops. And here we have two real negative eigenvalues. Eigenvalues are completely real. Both are negative. That takes us down this way, this way, and we have a stable sink. Let's say if they had opposing signs, it'd be a saddle point, which takes us back over here. It's not really a node. But let's say these guys had complex parts, meaning has something that looks like this. There's eyes. Well, that would suggest that it's a spiral, because only spirals have complex parts. There is no other type of node that is a spiral, that has complex parts and is not a spiral. It has to be a spiral. So if you do have a spiral, it's going to be in this conjugate form. And if you have this conjugate form, you look at the real part. A is our real part here. You don't look at the actual imaginary number. The imaginary number was just there to tell you that, hey, it's a spiral. But you want to look at the A's, the real parts. And it's the same exact thought process for determining whether it's stable or unstable. If the real part is positive, then it's an unstable source. If the real part is negative, it's a sink, a stable sink. There's one more tricky component to characterizing spirals, though, and that's determining what the orientation of the direction is. And it can be clockwise or counterclockwise. Something I've noticed is that every single problem we've dealt with for spirals has this kind of matrix setup where the off diagonal, one is negative, one is positive. So for W, if W is positive, you have counterclockwise rotation. If W is negative, it has clockwise rotation. For let's say W was negative, that would present this format. So this is the baseline format such that counterclockwise rotation, um, clockwise rotation would present as such. Oops. Um, I'm not 100% sure that it works every single time mathematically, but for every single problem we've had thus far in the class, it has proven true. Um, oh yes, next, more schematic problems. So this one is asking us to identify the coefficients for each schematic problem. And I kind of have a process to this. I'm not very good at puzzles, but if I can figure this out, then anyone can figure this out. So the first thing that we need to look at when it's asking us to identify A, B, C, and D is you want to look at the guys in the middle. The reason being is that for dx of d of t, there's only one y. That means whatever the value of b is for this y, that is b. So if we look at over here, and we look at y, it has to be 1.4. There is no other value of y affecting dx of dt. Likewise, for dy of dt over on the right-hand side, there's only one value of x. So if we look at the formula for dy of dt, it has to be 1.7. Now, since those have been characterized and the system only has 1.7 and 1.4 in it, that immediately implies that c and d are equal to 0. Uh, but that's not the case for number 5. So we repeat the same process. Um, we have a, b here in the middle. We have dx of dt, and dx of dt only has one y. So that means if we look at the formula for y, it has to be zero point 0.6. Likewise, for a, it has to be, where'd it go? Oopsies. Yeah, sorry. It has to be 0.9. Y of dt. For dy of dt, we look at this one. We look at this guy. It has to be 0.9. Because dy of dt only has one source of x. So you just look at the x. Next, we need to characterize c and d. If we know this guy is zero point 0.9, we know this guy is 0.6, that means that for dx of dt, this guy has to be the sum of zero point 0.9 plus some value c. Therefore, C is equal to 1.4. Well, technically, this should be a minus sign. With respect to the signs for these problems, the coefficients, their sign is arbitrary. It can be positive, it can be negative. It just depends on the way it's traveling. So try not to concern yourself with them. The actual variable x, that's what determines the positive slash negative sign with respect to the derivatives. All of the coefficients are going to have the same sign when you enter them into the homework. So notice how all of these are how all of these are positive. If you can set up the equation, you'll get the right signs. But when you enter them, they'll all be positive. Um, we can do dy dt really quick. We know that b has a value of zero point 0.6, and the for over here for y, dy of dt has a value of negative zero point 0.9. So that means zero point 0.6 in combination with something equals zero point 0.9, and that value is zero point 0.3. So we know d has to have a value of zero point 0.3. Like I said, it's kind of a puzzle. It doesn't involve a lot of math. Just kind of give it a shot and get a feel for it, and it becomes quite intuitive. So that's problems 1 through 5. I will cover 7 through 10 next. All right, part 2, numbers 7 through 10. We're predominantly dealing with two really annoying types of problems that are very long, very systematic. So I've defined a series of steps that help us solve the problem, and Dr. Varn also had a series of steps, but his were a little bit more long-winded and difficult to follow. So I've made it as succinct as it can be, which is not very succinct, but it's the best we have in this situation. So first off, we're dealing with non-homogeneous linear equations. What the hell is a non-homogeneous linear set of differential equations? Well, usually differential equations have some useful properties that allow us to blah, 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 solve a certain problem in day-to-day life, yada, yada. Well, it turns out the ones that are most useful have the phase plot centered around the origin, such that you have your dudes all coming to the origin. You have your pointer vectors all at the origin. It makes it very easy to deal with. Well, sometimes in our phase plot, the equilibrium point is not at the origin. Sometimes it's over, I don't know, in the first quadrant over here. This is very annoying, and it's apparently, I don't know, I'm not a mathematician, but apparently it makes them more difficult to work with and not as clear. So the idea of solving non-homogeneous linear systems is that we're taking the point that's somewhere not at the origin and we're moving it to the origin. We want it to be at the origin. So we go, okay, how can we get that point to the origin? Well, back in like seventh grade, you would have learned that you have some system, and if you have some point and you want to move it somewhere, you would take the x value and you would subtract some value, and that'd move it, say, to the right. Or you had y plus 7, and that would move it like to the left. The idea is the same. We have some value over here that we want to get rid of because this value is moving it away from the origin. We don't want that. We need to get rid of this guy somehow, some way. And that involves making an entirely new system of differential equations using some really bullshit algebra properties. It's really annoying, but here are the 5 steps. First, we find the equilibrium. So where is the guy in space? We find that. We find that location. Then we pose new variables. We go, okay, how can we get this guy to get to the origin? What can we do to him to get him to the origin? That's where we start to make our new matrix. Then, after we make our new matrix, after posing those new variables, we substitute it into a new system of equations. And then after that, we get a new matrix with a new general solution. After we get that general solution, then we turn it back into the original system, which is in terms of y of t here. And then from there, we can solve the problem. So just for clarification, we have a system, y of t, and we're going to turn y of t into something like, we'll say, z of t, using some really annoying properties. After we get z of t, we turn it back into y of t, so that way we can actually solve the problem. It's very unintuitive and it's very systematic. So like I said, here are 5 steps. We'll just jump right in. So first off, step 1 is find our equilibriums. So you're given this system. I just wrote it down here, and then you just turn that into 2 different equations. It's this part is very intuitive. You should know that these matrices and whatnot, they're really just systems of equations oriented in cute little boxes. So this guy, this guy equals this guy, and this guy, and this guy, and this guy. And then this guy's just right here. This guy's just right here. Same process. I'm sure you've done this 100 times by now. You just find your equilibrium. For this system, I found that I got this vector. This is my equilibrium position. I suppose it should really be written as this. It's not really a vector, but I don't know why I did that. But this is the equilibrium point. Now that we have our equilibrium point, we can make up some bullshit. So this is like pure out of our ass bullshit. Okay. This is where we say, let's pose some new variables. What can we do here? We can make our own system of equations such that we don't have this constant anymore. And we can use that with properties of the derivative. So I chose z. I choose my new variable to be z. And we can say that, remember when I said back in like 6th, 7th grade, you learned how to do this to translate some point on a plot like to the right or to the left. That's essentially what we're doing here. We are counteracting using this. We are counteracting this guy over here. This guy over here, he's somewhere over here in this quadrant. We don't want that. We want him to go over here. So see how it's a -5 and a +5? We're translating that point to the origin. Here's the point that I'm referring to, -5, 3, 0. That would be somewhere over here. If you had -5, 3, and 0, how would you get it to the origin? You would add 5, 3, and 0. Let's get them back over here. Plus 5, 3 over. So that's what we're doing here. So we choose a new variable. I chose z. So we have z is equal to y plus 5 over 3. This moves him back to the origin. This infers that in this phase plot, at the center, we have z. This is z. And we did that by manipulating y after we found the equilibrium point for y. We're just doing the exact opposite. So there's a couple of properties that are important for this. Off rip, the derivative of z is going to be equal to the derivative of y, because the derivative of a constant is just 0. So realistically, it kind of looks like this. And this gives us some useful properties that we're going to need very soon. We also know that since this is true, such that z is at the origin due to this modification, this also must be true. Because if we subtract 5 over 3 from both sides, we get z1 minus 5 over 3. We're going to need this in step 5. So here's our new variables. Our new system is going to be in terms of z, and z is essentially the same thing as y, except it has been adjusted to the origin, which makes it much more useful. The next part is number 3. We're going to substitute our z and y values into a new system of equations. So since the derivative of z is equal to the derivative of y, as we established over here, and we also know that y1, the derivative of y1, is equal to negative 3y1 plus 3y2 minus 5, which we got from over here, recall this, then we can say that since these guys are equal, we can just plug this into here. So z1, the derivative of z1 is equal to negative 3y1 plus 3y2 minus 5. And you might ask yourself, well, that's kind of fucking useless. Doesn't really do anything. Well, remember that we also defined y1 and y2 in terms of z. So after we do that, we can turn y1 into a system of z1 minus 5 over 3 plus 3 over z2 using this guy. So I took this guy and I plugged him right here because this guy satisfies this. Likewise, we also know y2 is equal to z of 2 right here. We can plug that guy into right here. And I'm not just making this up. I'm not just making this up. This is how Varn does it. This is how we were instructed to do it. It is some serious tomfuckery. So next, you're going to solve this. You're going to solve this for terms of z, and you'll find that every time you do one of these problems, the constant term and this guy, they're going to cancel out. Remember that we're trying to move some point to the origin, and we did so by solving the equilibrium and then offsetting it with some value that was equal and opposite. So these guys are always going to cancel out. They're always going to cancel out. And it's going to leave you with no constants. And you're going to have this brand new system from which you can extrapolate some data. And yeah, you have this system of z1, the derivative of z1, derivative of z2. And once again, this looks just like a matrix. And that's exactly the next step. Number 4, new matrix with new general solution. Here's our new matrix. It's a directly received from our new z's, our new system of z's. And we want to find the general solution of this matrix. Remember that we're going from terms of y to terms of z to z solution to y solution. It's like a whole cycle of z's and y's where you're kind of making your own system. Um, so here's my system of z, my matrix z, and you just do the same old, same old. You find your eigenvalues and you find your eigenvectors. My eigenvalues, I found them to be 0 and negative 6, and then you find your vectors from that, and then you just plug it in, and you're almost done. You're not done yet. This is only z of t. Remember, it goes bang, 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 bang. And right now, we're right here. So we have our general solution that we use from the general solution formula. And that takes us into next step, number 5, which is reinstate the old system. So we're turning it into a system of y's. Here's our system of z with respect to t. And remember, we had this strange list of things that we defined that we know are true just by basic algebra. And remember I said this would be useful in step 5? Well, that's where this comes in. Since we know z1 is equal to y of 1 plus 5 of 3, that implies that y of 1 is equal to z of 1 minus 5 over 3. In doing so, we can just take z of t, substitute it into y of t, And then we can get a whole new system such that these guys are just added. So perhaps I can make that more clear. Z of t is equal to y of t, such that you have your endpoint. So if I were doing this off rip, it would you have this guy is equal to this guy with the addition of this guy because this is true. If that kind of makes sense. So the very last part of the problem asks you to take the limit as t goes to infinity. And after you plug this in, this all becomes 0. And then you're left with your constant values and this system right here, which satisfies this guy right here. It all comes full circle. So yeah, very systematic, very tedious, very annoying. This problem is directly analogous to number 2 on the worksheet. Um, so if you want to give that a shot, I would recommend it. Next one, autonomous non-linear. So up until this point, we've been dealing with systems that can be characterized by lines. Linear meaning line. Well, now, if you look very closely, some of the variables, they're squared, and sometimes they'll be cubed. That means it's not a line anymore. It's a curve. And if you remember from earlier in the quarter or even towards the latter half of 17b, curves kind of present some problems. So we use a dumbed down means of finding their equilibrium points. And that's using this equation, or yeah, this is the linear approximation. I'm sure you remember it from the first midterm. So the first part is we need to find where the equilibrium point is. Remember, that's where everywhere's pointing. We need to find a point like that. That's step one. The next part is to use the properties of linear approximations to assess that equilibrium point. So let's say we had a graph. On this graph, we had a curve, and our equilibrium point was right here. That's what we're doing in step one. We are finding the equilibrium point. Step two is making a linear approximation at that point that's tangent to this point so that we can assess it. Because otherwise, we don't really have a way to, in theory, characterize this point and find out what type of node it is. So we need to use linearization. And once again, that's not an issue for the other problems because they used straight lines, and it's very easy to assess the tangent of a straight line. So here's number one, step one, equilibrium points. I found 2, I found 0, 0, and this big ass point, annoying point. If you read very closely, it tells you the point 0, 0 is an equilibrium of the following system. I did not read very carefully, so I did more work than I need to, but it's good practice nonetheless. Once you've done that, you can make your linear approximations. Recall this formula that we've been using for quite some time now. And recall that we have two equations here, and we need to do the linear approximation for both equations. So you're going to need to find the partial derivative with respect to f of x, the partial derivative with respect to f of y for each problem. So you're finding 4 partial derivatives in total. After you do that, you plug in the equilibrium point. So a b is equal to 0, 0. Because remember, the equilibrium point is where we're assessing the characteristic of the system, at which point in this example, that is 0, 0. So you plug in 0, 0, and you find that you end up with something like this. And guess what? that looks a lot like a matrix, and that's exactly what it is. That's what they're trying to get us to get to, a new matrix, which that leaves us directly with step three, establish a new matrix and determine the node type. Here's our new matrix as characterized right here, -8, -8, 4, 4. And then it's just asking you to identify the type of equilibrium. What type of node is it? Or not a node at all. And in doing so, remember all we need is our eigenvalues to do so. I found -7, -8. Um, uh-oh, oopsies. This should be +7. My apologies. I was writing too quick, which means this is a saddle point. But yeah, you just find your eigenvalues, and then you characterize the system. Now, an important point to note is that he's never going to have us do a bunch of mumbo jumbo like this for a nonlinear autonomous differential equation, because there's really no way for us to do it with the abilities that we have in 17C. So just know that we're probably just going to be asked to characterize it, provided the eigenvalues that we found. And yeah, that is homework 6. Like and subscribe for more, guys.